Hello everyone. In this tutorial, we are going to solve some of the linear algebra questions that are asked in the GATE exam in the previous year. So let's start with the question number 1. Question 1 says consider the system of linear equation. Okay, we have three equations in terms of x, y, and z, and here the one unknown k. So they are asking the value of k for which the system has infinitely many solutions. Okay, so here it is uh, typing mistake. Here it is in z, not 2. It is in variable z. So first of all, let's form an augmented matrix. Here we have 1 minus 1, sorry, minus 2. Here we have 3. On the right hand side we have minus 1. Here we have 1 minus 3, 4. Here we have 1. Here we have minus 2, 4, minus 6, and 1. Now we have to reduce it into echelon form. For that, we have to apply some row operation. So let's R2 minus R1 becomes our new R2, and R3 plus 2R1 become new R3. So what we are getting after that is just simply first row remain as it is. Now the second row, here we have 1 minus 1 from the first row, we get 0. Here we have minus 1. Here we have again plus 1. Now here we are getting 2 because we have multiplied minus 1 with this row and adding in this second row. In the third row we have here 0. Now here we have minus 4 plus 4 again 0. Here we have plus 6. Here we have already minus 6, so again 0. No, sorry, here it is 1. It is in k. We have to find the value of k. So here we have k minus 2. Now you can see that if this element will be 0, if k minus 2 equal to 0, then what I am getting is just simply 1 minus 2, 3. Here minus 1, 0, minus 1, 1, 2, 0, 0, 0, again 0. So now you can see the rank of the this matrix is equal to the rank of the whole matrix augmented. This whole matrix, considering this last column, it is also same as this rank, in which is equal to 2. And we can say here we have 3 unknown, sorry, x, y, and z. Here the rank is 2, which is less than the number of unknown. Here in our case it is 3. So we can say that the this matrix is rank deficient, and we have uh, infinite number of solutions if the this unknown k is equal to 2. So we have find our answer that value of k is 2, such that the system has infinite solution. Okay, let's solve question number 2. Question 2 says the value of p such that the vector, okay, we have a given vector, it is an eigenvector of the matrix. Okay, they're asking about this p. What is the value of p here in this matrix such that this vector will be the eigenvector of this matrix. Now here we have to first understand what eigenvector actually is. So here, if let's say any matrix A, and if I multiplied with any vector, now if suppose this x is an eigenvector of this matrix, then in the output what I am getting is just simply the same vector, but scaled scaled by some factor, which is lambda. Here in this case I am getting the same vector prior to I have the this multiplication. Okay, so here we can say if this condition is satisfied, we can say that the x is eigen a vector of A, and this scalar here lambda is eigen value of matrix A. So here, okay, so this is the necessary condition that a vector must have to satisfy to have it to have its eigen vector of this matrix. Okay, so here let's do the multiplication of this matrix and this vector. So let's write this matrix as it is. Here we have 4 1 2. Here we have p which is unknown. Here 2, here 1, here we have 14, here we have minus 4, here we have 10. Now let's multiply it by this vector. So we get 1 2 and 3. Now let's do the multiplication. Now here what we are getting is just 4 plus 2 plus 6. In the second element we have p plus 4 plus 3. In the third we have multiply this third row with this column. So we get simply 14 minus 8 plus 30. So let's do the sum of this all entries. So here what you are getting in the first element which is equal to 12. Here p plus 7. Now in the last what we are getting is simply 30 minus 8 which is 22 plus 14. We get 36. Now if this vector it is an eigenvector eigen vector of this matrix, then we can take out some scalar factor which is here the unknown lambda. Let's call it lambda. In the output we are getting the same vector which is here. We are getting the same vector here after taking the this scalar out from this vector. So let's write it 1. Write is 1 2 and 3. Now you can compare because these two vectors are same. So you can compare the first element and we can say that the lambda equal to 12 in this case. Now we have find out the value of lambda. Now compare this second element. So we can say p plus 7 is equal to 2 lambda. Now we already have find out the value of lambda. So put simply here and multiply it by 2. So we get 12 multiply with 2 we get 24. Now we are interested in finding the value of p. So let's simply subtract 7 from this 24. So what we are getting is just simply 17. Now if the here the unknown p has a value of 17, then we can say that this vector will be the eigenvector of this matrix. So we have find out the value of p must be 17. Okay, so we have value of p is 17. Okay, now let's solve question number 3. Question 3 says the value of x for which the whole eigenvalue of a matrix is real. Okay, they are asking about this value of x such that the eigenvalue of this matrix are real number. So here you can see that this matrix has a complex entry, complex element, complex number in its uh, a 1 2 position. So we can if you know that the if let what is the Hermitian matrix, if let defined Hermitian matrix. Okay, so what is the definition of Hermitian matrix? It simply states that if the any vector A has exactly the same as its complex transpose, then we can say the given matrix is Hermitian. Okay, Hermitian matrix is only defined for the complex number. In the real, for the real number we have a symmetric and skew symmetric, and for the complex number we have a Hermitian and skew Hermitian. Now the Hermitian matrix has another property is that if a matrix A is Hermitian, Hermitian matrix, then its all eigenvalues must be real. Okay, this is the another property of the Hermitian matrix. If the any matrix it is an Hermitian, then we can say that all its eigenvalue must be real, and that they are asking in the question value of x for which the eigenvalue of the matrix is real. Okay, so now we have to make this matrix as an Hermitian matrix such that the eigenvalues are real for this matrix. So let's use this condition to make it Hermitian. So here, let's first of all find the complex conjugate of this matrix and then take the transpose and it with equate it with the initial matrix. So let's first take the complex conjugate. Now in the complex conjugate, we have to just simply change the sign of this imaginary part. For example, I have entry a plus ib, then it is an a. Now I am interested finding in the a conjugate. So I have just uh, put here minus in the place of plus and write as it is. So I have find out the conjugate of this element. Similarly, in the same manner, I have to just uh, put the minus sign in front of imaginary part or change the sign of imaginary part that is available in this matrix. So let 10 is a real. So as it is because it is a real. So conjugate is does not affect this real number. So here we have 5. Okay. Here we have complex. So we have uh, change the sign and write as it is. Here you have real value. Okay, x. We don't know x. So let's assume we are denoting the conjugate by the bar or a number. So we can say that x bar it's represent x conjugate. Here the 20 is real, so 20 as it is. Here 10 is real, 2 sorry 2 is real, so 2 as it is, and 4 real, 2 is also real, minus 10. Okay, so all the remaining entries are real. Now we have to take the transpose of this conjugate. So a conjugate transpose. So now what we are getting is just simply 10 5 minus j. Here we got what is 4. Here x conjugate 22. Here 4 2 minus 10. Now we have to just use the definition of this Hermitian matrix. Now just simply equate this matrix with our initial one that is given in the question. So 10 5 plus j, here 4, here x 22 4 2 minus 2. Now you can see all the corresponding entries are the same. Here 2, here 2, here minus 10, here 2 2 4 4. Now okay, all the remaining entries are the same. Now we can compare this also with this. So we can say value of x is equal to 5. This element is equal to so 5 minus 6. So we have find out. We can also find out from here because here it is an x conjugate. So we have to change the sign in order to find the x. We are going in the reverse direction because we are finding the value of x. So we can also find the same value from this element. Okay, so we have find out the value of x such that the all the eigenvalue of this matrix will be real. So x is given by 5 minus j. So option D is the correct answer. Okay, let's solve question number 4. Question 4 says for a matrix we have given matrix A 1 10x minus 10x 1, and they are saying the what is the determinant of A transpose times A inverse. Okay, so first of all let's find A transpose. So here we are given A, so we can easily find its transpose. So that A transpose will be, we will just simply make the row as a column and the column of this matrix is a row. So we can just simply get 1 10 of x minus 10 of x here 1. Okay, so we have find out the transpose of this matrix. Now we also need the inverse of this matrix. So here it is a 2 cross 2 matrix, so it is easier to find the inverse for the 2 cross 2 matrix. So here the definition of this inverse is simply just 1 upon determinant of A into adjoint of this just matrix A. Okay, so here the determinant of this matrix is just simply uh, we have to multiply this element and subtracting multiplication of this element. So what we are getting is just determinant is 1 plus 10 square of x. Now we have to find the adjoint of A. Now in the case of 2 cross 2 it is easy to find the adjoint of a. What you have to do is just simply reverse this, and this element, is goes to here, and this element is come here. So here we get, here the both elements are identical, so does not change in the diagonal. So now, and here we have just simply changed the sign, make positive if it's negative, and make negative if it's positive. So here what we are getting is simply minus 10 of x, and here we are getting plus 10 of x. So we also have find out the A inverse. Let's little simplify little bit. So here we can use the identity, sec square of x minus 10 square of x is equal to 1. So we can say that it is nothing but sec square of x. Now the remaining matrix will be remain as it is here. So 1 minus 10 of x, here 10 of x, here 1 as it is. Now we have find out this A transpose and A inverse both. So let's do the multiplication of both and find the resultant matrix. So it is transpose here. So let's write this matrix 1 minus 10 of x, here 10 of x 1. Now let's write this matrix 1 minus 10 of x, 10 of x and 1. Now all we have to divide by simply sec square of x. So let take in the front sec square of x. So let's do some simplification and multiply this, multiply both this matrix. So we are getting as a simply sec square of x into we have here we have to multiply this column, this row with this column. So we are getting 1 minus 10 square of x is the first element. In the second element we have to select this first row multiplied with this column. So here we are getting 10 of x minus 10 of x will be minus 2 10 of x. Now in the third element we have to select this second row multiplied with this first row, first column, sorry. So in the output we are again getting the positive 2 10 of x. Now for the fourth element we have to select this second row and this second column. So here we are getting again the same as we are get here. So it is 1 minus 10 square of x. Now we have to find the determinant. So let's determinant of A transpose A inverse. Now so what we are getting is simply just okay. So let's find the determinant of this resultant matrix. So here we have to find the determinant of this matrix. Now the next step, be careful, you may make the mistake. Let check for the determinant. Here this factor, if we take out from this determinant we have to square this because it's multiply with this first row and multiply it with this second row. So we have to uh, square it for the taking out from the determinant. So what we are getting is simply just 1 upon sec 4 sec x to the fourth power, okay, and the remaining in the form of determinant. So 1 minus 10 square of x minus 2 10 of x, here 2 10 of x minus here 1 minus 10 square of x, okay. So okay, we use here property is that if we are finding the determinant of k times this matrix A, and this if this A matrix has a dimension of, if this A matrix has a dimension of 2 cross 2, so we can say that the determinant of k times A will be the same as the k square, sorry, here k square times the determinant of A. We have used this property here to find the determinant. So let's simplify again. So here what we're getting is simply just sec of x to the fourth. Now here what we're getting just 1 minus 10 square of x whole square. Here we get multiplication of this multiply with minus 1, so we get plus 4 10 square of x. Now expand this square, so we are getting just simply 6 square of x whole square. Now here minus 4, not 4, sorry, 2 tan square of x plus 10 of x raised to 4. We have already 4 tan square x is there, so 4 tan square of x is already there. Now you can see the 2 tan square of x is cancelled with from here, so we get 2. So what we are getting is just simply 1 upon sec of x square to the square. Here we get 1 plus 2 tan square of x plus 10x square whole square. Now you can see it is the nothing but the expansion of 1 plus 10 square x. So sorry, I am running out the space, so I can rearrange it in this small space. So sec square of x whole square. So here what we are just simply getting is 1 plus 10 square of x to the whole square. Now 1 plus 10 square of x is again sec square. So what we are getting from there, let's write here. So we are getting is just simply sec square of x, x whole square divided by sec square x. Okay, so we just simply cancel out it and we get 1 1 as our answer. So we can say the option D is the correct one for this question. Here, here x is comes here. There is a mistake in the writing in the option. So here x is there. So but does not make any change. Is the option correct one is the D for this problem. Okay, let's solve question number 5. Question 5 says the sum of the diagonal element of 2 cross 2 matrix is 6 minus 6 and the maximum possible value of the determinant of the matrix. Okay, here we have given the matrix is 2 cross 2 is the dimension and the trace is given minus 6. Now we know from the properties of eigenvalues that the trace of the any matrix is nothing but the sum of its all eigenvalues. So here we have two eigenvalues because it is a 2 cross 2. So lambda 1 plus lambda 2 equal to minus 6. Okay, this is the given in the question and they're asking then the maximum possible value of the determinant. Okay, so we have did similar problem in the one of our other another video. So you can if you haven't watched this video then you can go back and watch this. So here we have find the determinant. So we have just multiply with lambda 1 with lambda 2. It is the another property of eigenvalue. So now here you can remove this lambda 2 and put in the terms of lambda 1 from this equation. You can make lambda 2 in subject and you can rearrange like this. Now put this value lambda 2 value in this determinant equation. So we get determinant will be equal to lambda 1 times minus 6 minus lambda 1. Let's do the multiplication minus 6 lambda 1 and minus lambda 1 square. Okay, now they are asking about the maximum possible value. So we have to take the derivative of this d with respect to lambda 1 because here the lambda 1 is our variable. So let's take the its differentiation. So we get minus 6. Here we are getting minus 2 lambda 1. Now we want to find the stationary point. So we have to equate this del d by del lambda 1 equal to 0 for the stationary point and find the value of lambda 1 from here. So we can say 6 equal to minus 6 equal to 2 lambda 1. So here we get lambda 1 will be minus 3. Now to make sure that this stationary point is corresponding to the maximum, so let's differentiate again this equation. So del square d by del lambda 1 square. So let's take again the differentiation of this equation. So we are getting minus 2. Now it is negative. So we can say that this point is corresponding to the maximum value from the calculus. basic theorem of calculus. If any function has its double differentiation is negative at that point, then it is at a maximum value. Okay, so for finding the maximum value, you can also find the value of lambda 2 from this first equation. We have given the sum is -6, so you can derive lambda 1 here. You can also get -3. Now we have to find the determinant, which is x of all other possible value. So we have to just multiply this two value here. So -3 multiply with -3, so we are getting 9. Maximum determinant possible for all the true cross to matrix such that it trace will be -6. It is +9. Okay, so our correct answer is +9. Okay, let's solve question number 6. Question 6 says, if we have a set of three a linear equation and three unknown. Okay, we have three linear equation and three unknown. Okay, and here x equal y means x and y are equivalent statements. Okay, and x is not equal to y means x and y are not equivalent. Okay, so here we have given the notation. We have given what is not equal to and equal to represent. Equal to represent that this p statement and q statement are equal, and are not here not equal to represent this q statement and r statement are not equivalent. Okay, so here we have given a three linear equation and three unknown. Okay, so let's go one by one. So statement P says there is a unique solution. Okay, statement P says that this for this system we have a unique solution. And then Q statement Q says the equation are linearly independent. Okay, so what Q means simply that if all equation are linearly independent, then we have determinant of this coefficient matrix will be other than 0. That means which is non-singular. Singular, we know from the basic concept that if the all or the line of any matrix are linearly independent, all the line are linearly independent, then the determinant must be non-zero. So we can say that the determinant of these three equation uh, of coefficient matrix from these three equation will be a non-zero number. So we can say that the system has unique solution for this condition also. So statement P is also saying the same thing. There is a unique solution. So P and Q are the exactly the same statement in the they are saying only in the different language. So let's check option R. Option R says all eigenvalue of the coefficient matrix are non-zero. Other again the same statement in the different words. What they are saying the all eigenvalues of the coefficient matrix. Okay, here we have written this ax is equal to b. Here a is our coefficient matrix. Coefficient matrix. Okay, so they are saying that all the eigenvalue of this matrix A are non-zero. If suppose let's say any one eigenvalue of this matrix is 0, then what happen if we are trying to find the determinant of this coefficient matrix, then we know it is nothing but the multiplication of all eigenvalues. Now suppose at least one is 0, then we find that determinant is 0. Okay, so we can say that the determinant is 0. That means at least one of these rows are linearly dependent. So the option B, option R, all the eigenvalue of the coefficient matrix are non-zero. Okay, it is also same for the this condition that the any matrix is non-singular. So all the eigenvalue are non-zero. If any one is 0, then the determinant will be 0 and the matrix will become a singular. So option R is the also the same statement. It is indicating that the system has a unique solution. If this condition is hold, the system has unique solution. Now the a statement S state the determinant of the coefficient matrix is non-zero. Again, this same condition. If the determinant is non-zero, then we have a unique solution, which is same as statement P. So statement S is also equivalent. So all four statements are saying the same things in the different language or in the different words. So we have to select the option C because the four statements are equivalent to each other and they are indicating the same thing. Okay, let's solve question number 7. Question 7 says if the two columns of the determinant of this P, okay, we have determinant given. If we are interchanging these two columns, let's suppose this either we change this first column or second column or third column, any of these three, we have to change the two. The if the two column of the determinant P are interchanged, which from the following statement is true? Okay, so we have to finding the which of the following statement is correct regarding the value of determinant is correct. Okay, so we have to find the correct statement. Now we know from the basic concept, if the let's say we have any matrix here and we are finding the determinant, and if we interchange this either the row or the uh, column of any matrix first time, uh, then we know that its magnitude does not change, but its sign will be changed. If the determinant of this matrix is positive, then after changing this row with this row, we get the negative determinant. Okay, but the value still remain as it is. They are asking about the uh, column uh, interchange, but it is the same thing as the row interchange. So we have to choose the correct option. From the option A says the both absolute value and sign will change. Not option A is not correct because absolute value does not change, only sign will change, and absolute value remain unchanged but sign will change. Okay, option B is the correct statement according to property of the determinant. And the option C says uh, absolute value and sign will remain unchanged. No, sign will change. The option C is not correct. The option D says absolute value will change but sign will not change. Again, option D is the false. So only the correct statement is option B. Okay, let's solve question number 8. Question 8 says the lowest eigenvalue of a 2 cross 2 matrix. Okay, they are asking about the lowest eigenvalue of this matrix. So let's form just then first A minus lambda I and then find the determinant and equate is equal to 0. So let first of all form this matrix. So we have just 4 minus lambda, here 2, here 1, here 3 minus lambda. Now let's find the determinant of this matrix and equate is equal to 0. So what we are getting is just simply 4 minus lambda multiplied by 3 minus lambda minus 2 equal to 0. Now let's do the multiplication. Here we are getting 12 minus 3 lambda minus 4 lambda 7 lambda plus lambda square minus 2 equal to 0. Now you can rearrange lambda square minus 7 lambda plus 10 equal to 0. Okay, and let's solve for the lambda. Let's use equation. Okay, we will get plus 7 plus or minus under root of b square minus 4ac. Here b is minus 7, so square it 49 minus 4ac. Here our c is plus 10 and a is 1, so we get here 40. Now divided by 2a, we are just simply getting 7 plus or minus here under root 9 divided by 2. Now we are getting 7 plus or minus 3 by 2. Now if we solve, we are getting just uh, lambda equal to 5, lambda equal to 2, and they are asking about the lowest, so we have to select the lower one. So we have the eigenvalue which is 2 corresponding to the lowest value. Okay, let's solve question number 9. Question 9 says for the given matrix, okay, we have given matrix P where I is under root of minus 1, which is an imaginary part, the inverse of the matrix P. Okay, they are asking about the inverse of this matrix. So we know how to find the inverse. Here it is a two cross two matrix, so it is easier for us to find the inverse. So let's first of all write the equation of inverse. Nothing but 1 upon determinant of P into adjoint of this matrix P. Okay, so here we first of all we have to find the determinant of this matrix. So let's find it. So we have just simply 4 plus 3i multiplied by 4 minus 3i. Here we have minus plus I square. So let's, okay, it is nothing but a plus b and a minus b. So it will be 4 square minus 3i square. Here plus I square remaining. So here we are getting 16. Where here we are getting 9 I square. I square will be minus 1. So we are getting plus 9. Here we are getting minus 1 from here this I square. So after that we are simply just getting 23. No, okay, sorry, not 23, 24, because 16 plus 9 will be 25 minus 1 will be 24. Okay, so we have find out the determinant of this matrix will be 24. Now we have to find the adjoint of this matrix. Now here it is a 2 cross 2 matrix. So now it is easier for the 2 cross 2 matrix. We have to just simply, what to do is just simply this element is goes to here and this element comes here. Okay, so let's do, we have to 4 minus 3i and this element will come here. So we have 4 plus 3i. Now we have to just simply change the sign. If here it is positive, it is negative, so we have to make it positive. Here if it is positive, we have to make it negative. So here we are getting simply I, here minus I. Okay, so we have find out the adjoint of these two cos2 matrix and divide by this uh, determinant. So we are getting the inverse of matrix P. Let's check the option. So option A is the correct one according to our this inverse. You can also find, if you don't know this trick how to change this element and how to change the sign, then you can also simply find this just finding this minor of this element. Okay, let's find minor of this one will be 4 minus 3i. Now the minor of this 1 2 will be just simply I. We have to just delete this row and this column for finding the minor of this. So we have I. Okay, the minor of 1 2. We have to just delete this because we are finding the minor of this. So we have to find, delete this column and this row. So we are just simply get minus I and the minor of 2 2. So we have to delete this second row and second column. So we are getting just simply 4 plus 3i. Now we have to uh, multiply it with the sign factor for the finding the cofactor, and we have to take the transpose. Then we are getting the adjoint of this matrix. You still get the same matrix. Okay, let's move to the problem 10. Okay, problem 10 says at least one eigenvalue of singular matrix. Okay, they are asking the eigenvalue, at least one eigenvalue of singular matrix. Now first of all, what is singular matrix? If matrix A is singular, then determinant of matrix A will be 0, and then it will be singular. If the determinant of it 0, of it, if this matrix is 0, then we know from the properties of eigenvalue, determinant is nothing but the multiplication of all the eigenvalues of any matrix is equal to determinant of A. Here it is given the matrix is singular, so determinant is 0. Now from here we can see that either lambda 1 or lambda 2 or lambda 3 or maybe any value from the lambda n equal to must be one of this value will be 0. What this is they are asking. So at least one eigenvalue of a singular matrix will be 0, and then it will be a singular matrix. Okay, so okay, that's it, and thanks for watching.